In my earlier lecture, we talked about the time series forecasts, which included the naive approach, the moving average approach, the weighted moving average approach, and the exponential smoothing. Now we're going to switch gears and talk about the associative model forecasting technique. In an earlier example, we said that every time we noticed Bobby with an umbrella, we noticed that it was raining. And so one day, even without knowing what the weather was, we see Bobby holding an umbrella, and so we can make a prediction that it is raining outside. With the associative model approach, we use observations over a period of time, known as predictor or independent variables. In this case, the fact that every time we see Bobby holding an umbrella, we notice that it's raining. And then we use the simple linear regression to make our prediction, which means that we take all of our observations, which is our predictor variable, we put it into our simple linear regression, and then that will output our forecast. The difference from the time series is that this is not based upon time, but rather the association from two different variables. Now let's deep dive into the simple linear regression. And here's the formula for the linear regression model, which should look a lot like the linear trend equation we learned earlier. Let's take a closer look at each component using an example. Say we own an ice cream shop and we're interested in forecasting the sales of ice cream dependent on weather. So let's draw this out. Here we have our X and Y. Because we are forecasting sales dependent on outdoor temperature, the temperature outside will be our X value, and Y will be our sales of ice cream. What we are saying here is that our sales are dependent on our temperature, which is the X value. And say we start collecting the data of sales that we make at different temperature levels, and we start seeing something that looks like this. And when we get the average, we see a pretty obvious trend that as the temperature increases, the sales of ice cream increases. Using Excel's regression report, which we talked about in an earlier video, we can now discover A, the y-intercept, and B, slope. And applying the data that we collected in sales and temperature, we can now determine the value of this line. This means that we will now be able to forecast sales according to the temperature outside. If the temperature is, say, this amount, then we know that we can expect sales to be at whatever this amount will be. Okay, now we're ready to take a look at a linear regression example. A little trick to help you identify questions that are related to linear regression modeling is if X, then Y. In this case, we are saying if the price of a lobster is $6, then we can expect to sell 200. As another example, we're saying that if the price of a lobster dinner is $9, we will only expect to sell 140. Therefore, the independent variable X is the price, and the dependent variable Y is the average sold. Now there will be three types of things you'll be asked to do with such a question. First, you'll be asked to create the model. Then, once you have the model, you'll be asked to make a forecast. And then finally, you'll be asked to evaluate how good or poor your model is. Let's start with learning how to create a model. In order to create our model, we need to discover the y-intercept and the slope of this data set. Not to be repetitive, but X is our independent variable, which in this case is price, and Y is our dependent variable, average number of sold per day. As I said in a previous lecture, you will not be responsible for manually calculating A and B. And if any questions require A and B, you will be allowed to use Excel. In order to save time, here I've already generated the Excel summary report. For those of you who don't remember how to do this, you go to Tool, Data Analysis, and then you select the regression option. As always, let's first write out the formula. Now that we have the template for our model, let's start creating it. And as I said in an earlier video, A, the y-intercept, can be found right here. So in this case, A equals 3, 1, we'll round up to 6, 316. Plus B, which is the slope. The slope can be found right here. So we enter that number. So because it's a negative, we'll do minus 19.51 x. Now we have our model, which is y equals 316 minus 19.51 x. Now say for whatever reason, the price of lobster has gone up to $10. Now using our model, how many lobster dishes can we expect to sell at $10 a piece? To answer this question, we simply solve for y using 10 for x. So y equals 316 minus 19.51 times 10. So y equals 120.9. You can't sell a 0.9 lobster, so our answer is 120. At $10, we are forecasting to sell 120 lobster dishes. Now let's look at analyzing how good of a model we actually created. The first gauge of how good of a model you have can be found in the standard error section of the summary output. The standard error is a measure of the scatter of points around the regression line. So what this measures is how far from the line of regression does our actual data sit. In this case, on average, and looking at all of our actual data, we are 3.786 units off from our linear model. The second measure is the R-square value. R-square is a percent measure of the strength of the forecast of y with respect to x. An example of a good predictor would fall between 0.8 and 1. 1 meaning that the two variables are 100% correlated. A poorly correlated regression would have a lower R-square value, say somewhere around 0.25, and 0 saying that the two variables are absolutely not correlated with each other. And that wraps up our video series on Chapter 3, Forecasting.